Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired and refreshed. Now, if you find my videos interesting and important to your studies, also please don't forget to subscribe. So here is an example of moment of a force about a point, and I solve this into two ways, one by scalar approach and the other by the vector approach. So determine the moment of the three kip force about corner B of the bent bar. So this is the bent bar and this is B. So we resolve the three kip force into components. We have 8 and 6. So 4, 3. So 5 hypotenuse. So therefore the vertical component is 3 times 6 over 10 or 3 times 3 over 5. And that is equal to 1.8 kips, and the horizontal component going to the negative y direction is 3 kips times 8 over 10 or 3 times 4 over 5, and that is 2.4 kips. So imagine we have bx, by, and bz axis. So the positive moment would be, by right thumb rule, would be in that direction. That's sense. So since the 1.8 kip is on the plane xz plane, same as B, then it has no moment. It crosses the x-axis. Only 2.4 kips will have moment about px. However, the direction of the moment is opposite, so it is negative, negative 2.4 times 12. So mbx is negative 2.4 times 12. So it is negative 28.8 kip inch. MBY by right thumb rule would be the sense here. This is parallel to the y-axis, so it has no moment. Only 1.8 will have moment about the y-axis, and it is negative again. Negative 1.8 times 8, and that is equal to negative 14.4 kip inch. Then MBG, this is the positive sense by right thumb rule, the curling of your forefingers, your right thumb pointing towards the positive z-axis, and the 1.8 keeps it parallel to the z-axis, so no moment, only 2.4. But the moment of the 2.4, imagine this is the z-axis, is opposite to that of the positive sense. So therefore, the moment about BZ is negative 2.4 times 8, and that is equal to negative 19.2 kip inch. So therefore, in vector form, the moment about B is negative 28.8 I, negative 14.4 J, negative 19.2 K kip inch. Then by vector approach, the moment about B is MBD or RBD cross the force. So MB is RBD position vector from B to D cross the force, and BD is negative 12 along Z, positive 8 along X. So 8I, 0J, negative 12K, negative 12 along Z, forward, positive 8 along X. So no movement along Y. Then these are the components of the force. No X component. The Y component is negative 2.4. The Z component is positive 1.8. It's upward. Then the unit vectors copy the elements of the first two columns. So for moment about X, 0 times 1.8 I, so 0, then minus negative 2.4 times negative 12, which is positive, but that's negative in that direction, so negative 2.4 times 12. So that's why you have here negative 2.4 times 12, so it's correct. Then along Z, 0, then minus 1.8 times 8. So again, it's negative 1.8 times 8, which checks here. Then along K, 8 times negative 2.4. So negative 8 times 2.4. It checks, then minus 0, because that's 0. So therefore, the moment about B is the same, negative 28.8I minus 14.4J minus 19.2K. Kip inch. Then for your part, determine the moment of the 3 kip force about end A of the bent bar. So this is end A, and I hope that you'll now have an idea how to compute the moment about A. Solve that in two ways also, by scalar approach and by vector approach. Vector approach, and show that this is the answer. So problem or example 72. The tensions in cables AE and BE are 400 pounds and 500 pounds respectively. Determine the moment about corner D of the force each cable exerts on the trapezoidal plate. So again, I'll solve this into two ways, scalar approach and the vector approach. First, let's have the tension in cable AE, which is 400 pounds. And let's resolve that into components. So FAE is 400 times its directed negative 40I, then positive 40J, positive 20K, negative backward along X, rightward along Y, and upward along Z. So these are the components. Then square root of 40 squared plus 40 squared plus 20 squared. FAE therefore is negative 800 over 3I, positive 800 over 3J, positive 400 over 3K pounds. Then these are the components. Then first, along dx, since the force acts on dx axis, obviously moment about dx is 0 by the scalar approach. Then about y, by right thumb rule, the positive moment would be, in that sense, this passes through dy parallel, so only 400 over 3 will have moment about dy axis, but the positive sense is in this direction, but the moment is in that direction, therefore moment about dy is negative 400 times 40, and it is equal to, moment about dy is equal to, in decimal, negative 5333 pound inch. Then moment about dz, the positive sense is in that direction, so 0 passes through dz, no moment because it is parallel to the z-axis, only 800 over 3, this one, along y, will have moment about z, and the positive sense is in that direction, and it's this in the same direction. So it is positive 800 over 3 times 40 mdz, and it is equal to 10,667 pound inch. Therefore, the moment about D due to the tension in cable AE is equal to negative 5333J plus 10,667 pound inch. Now for the tension in cable BE, in vector approach, it is R moment at D, so RDA cross the force. It is also RDE cross the force, but the simpler one is RDA, so that the position vector dA is just 40I. So 40I 0, 0, J, 0J, 0K. Then components of the force, unit vectors, then copy the first two column elements. So let's check. Along I, 0, then minus 0. So that's why moment along dx is 0. Along J, 0 times negative 800 times 6, so 0. Then minus 400 over 3 times 40, so that's negative 400 over 3 times 40. So negative 5333, it checks along y. About y, then about the z-axis, 40 times 800 over 3, positive, then minus 0, so positive 40 times 800 over 3, which is this. So 10,667. So it checks moment about point D due to cable AE, or the tension force in cable EE is negative 5333J plus 10,667K. Now for portion VE, the force is 500 pounds and it is directed backward 40, upward 20. So in vector form, 500 times negative 40I plus 20K over square root of 40 square plus 20 square. So the components are along X negative 447.21, along K, along Z 223.607. So let's transmit it. This is the X component and the Z component is upward, and this is point D. So moment about the dx axis positive in that sense. So this is parallel. So this is same sense. So positive 223.607 times 40 inches. 40 inches. MDX equals 223.607 times 40, and it is positive 8944 pound inch. MDY about this axis here, positive in that sense. So this horizontal component passes through dy, so 0. This one is negative because the positive sense about dy is in that direction and it is in the opposite direction. So negative 223.607 times 40 inches moment about dy, and it is negative 8944 pound inch. Finally, moment about dz, the positive sense is in that direction. So this is positive because it is in the same direction, parallel, so 0. So positive 447.21 times 40 inches mdz. And in vector form, the answer moment about D due to cable, the tension in cable BE is equal to 8944I minus 8944J plus 17888K pound inch. That's by scalar approach. Now for the vector approach, it is RDE cross the force or RDB cross the force. I'll use RDB cross the force for the vector approach. So MD is RDB cross the force, where DB is forward 40 along X, rightward 40 along Y. So 40I, 40J, then 0 along K. Then components of the force, unit vectors, then copy the first two column elements. So let's check along I, 40 times 223.607 minus 0. So it's the same as before. Then along J, 0, that's 0, minus 223.607 times 40, so it is negative. Then along K, 0, then minus negative, so positive. So for cable BE, moment about D is 8944I minus 8944J plus 17888K. So that's it. Then for your part, this is your problem. The tension in cables A and BE are 400 and 500 pounds respectively. Determine the moment about corner C, this is corner C, of the force each cable exerts on the trapezoidal plate. So since I resolved the forces into components already, I hope that you know how to compute the moment by the scalar approach and the vector approach. So check that for cable AE, the moment about C is negative, is given by that answer. And for cable BE, moment about C is given by this answer. So that's it for this second problem. So for problem 73, A 1.5 kilonewton force is applied to the pipe assembly as shown. Determine the moment of this force about end A. So this is end A. So let's resolve the force into components. Horizontal along Y negative 1.5 cosine 53.13 degrees, and that is 0.9. Then 1.5 sine of 53.13 upward, that's 1.2. So the force is now removed. We replace the force by its components. Then this is AX, AY, AZ. So let's have our guide. By the way, tangent of 53.13 degrees is 200 mm divided by this distance. Therefore, this distance is 200 divided by tangent of 53.13, so 150 mm. So expressing the unit of distance in meter, 0.3, 0.2, then 0.3. So this is the positive sense of moment about AX, positive sense of moment about AY, and positive sense of moment about AZ. So if we look at the figure, only 1.2 is positive and zero point 0.9 is negative. It is opposite to that sense. So 1.2, the moment arm is 0.3, 150 plus 150 or 300 mm or 0.3. Then minus 0.9, the distance, this distance is 200 mm or 0.2. So MAX is 1.2 times 0.3 minus 0.9 times 0.2. And it is 0.18 kilonewton meter. MAY, so this is parallel, so 0, 1.2 has moment, but it is opposite to this sense. So it is negative 1.2 times 0.3, this distance here. MAY is negative 1.2 times 0.3, so negative 0.36 kilonewton meter. MAG, this is the positive sense. So parallel, only 0.9 will have moment about the AZ axis, but it is opposite because it is in that sense. So rotation would be in that sense. This is the positive sense. So it is negative 0.9 times 0.3 because A, B, C lie on the YZ plane. So the moment arm of 0.9 about the Z axis is 0.3. So negative 0.9 times 0.3. That's MAZ. So negative 0.27 kilonewton meter. So MA therefore in vector form is quantity 0.18I minus 0.36J minus 0.27K kilonewton meter. And then by the vector approach, so it should be RAD cross the force, where RAD is rightward, so along Y 0.3, downward along J negative 0.2, forward along X 0.3. So 0.3I, 0.3J, negative 0.2K. So components of RAD, so 0.3, 0.3, negative 0.2, components of force, then unit vectors, copy the first two column elements. So let's check and expand first with I. 0.3 times 1.2I minus negative 0.9 times negative 0.2, so that's positive, but that's negative direction. So 0.3 times 1.2 minus 0.9 times 0.2. So it's 0.3 times 1.2 minus 0.9 times 0.2. So it's 0.18 I. Along J0, then minus 1.2 times 0.3. Minus 1.2 times 0.3. So it checks. Then along K, negative 0.3 times 0.9 minus 0. So negative 0.3 times 0.3 times negative 0.9. So it's the same in this. Therefore, the answer moment A is quantity 0.18I minus 0.36 J minus 0.27 K kilonewton meter. Then for your part, same problem. And this time, determine the moment of this force about joint C. So it's easier. It's very close. Give you idea, moment about CX is 0. So show that the answer is negative 0.36J minus 0.27K. That's why there's no X component.